Hi everyone, and welcome to the second of two videos going through some past exam questions on redox titrations, specifically involving manganate ions. So this first question here is asking us about the electron configuration of a vanadium ion. So for this one, this is really a transition metals question. So if you're looking at this for redox titrations, you may not have covered this yet, but we'll go through it anyway. So what we're going to do is we're just going to carry on doing the electron configuration. So it's 2s2, 2p6. So next thing would be 3s2, 3p6. And then what would come after 3p, remember, would be 4s, because the 4s fills up before the 3d. So we just did it would be 4s2. And then vanadium, if we just look on our periodic table, let's find our vanadium. So vanadium here, this would be our 4s2, so vanadium would be 3d3. Okay, so it'd be 4s2, 3d3. That would be our normal vanadium, but then it's telling us we want a vanadium ion in the +3 oxidation state. So it's going to be vanadium 3+. So it's going to lose 3 electrons, but although the 4s fills up before the 3d, it also empties before the 3d. So we're going to get rid of the 4s electrons. That's going to get rid of 2, and then we're just going to lose 1 from here. So it'd be 3d2. Suggest why vanadium does not form ions in which vanadium has an oxidation state greater than +5. So if this is the +3 oxidation state, then +4 would be blah, 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 3d1. +5, you'd have got rid of the 3d altogether. And so to have something higher than +5, you'd have to be getting rid of the 3p electrons. Okay, and those are just going to be much more difficult to remove. Okay, so it's only a 1 mark question here. So all it wants us to say is why don't you get oxidation states greater than +5? Because vanadium has 5 electrons in the 4s and 3d subshells. And those are the only electrons that we're going to be removing. Okay. We could say it would require too much energy to remove electrons from the 3p subshell, because they're going to be more strongly attracted to the nucleus. But that's really a transition metals kind of question, so you may not have covered that yet, so I won't worry too much about that part. This is where we get into the actual redox titration, so let's see what it's saying here. Again, it gives you quite a lot of information. Okay, so a sample of vanadium metal is reacted with acid to form a yellow solution. It's made up to 50 centimeters cubed. This contains VO3- ions in the +5 oxidation state. This yellow solution is reduced to form a violet solution containing VN+ ions, okay, which we don't know what that is. 50 centimeters cubed solution contains vanadium in the +N oxidation state. 10 centimeters cubed of this solution is titrated with potassium manganate. 13.2 centimeters cubed are required to reach the end point. Okay. The VN+ ions are oxidized back to VO3-. Okay, that's fine. So it's going to go back to this one. And the MnO4- ions are reduced. Okay. Why is there no clear colour change at the end point of this titration? So the problem here is that you've got these ions that are similar colours. So it's telling us that the VN+ ion is a violet solution, okay, and we should know that the manganate ion is also a purple colour. So this is what's going to cause the problem in terms of trying to spot a colour change. So it's only 1 mark, so we can say that the VN+ is violet and the MnO4- is purple. Right, that's it. That's all we need to put there. Okay, what's the question saying here then? This is the question, this follows a very similar pattern with these redox titration questions, where you have like a whole bunch of information and then a whole bunch of blank space to do a lot of work in. So they kind of follow the same pattern, these questions. Right, analyse the student's results, determine the value of n in Vn plus. Right, makes sense. So they want us to work out what ion this is and then construct an equation. Okay. Right, where are we going to start? It's going to be awkward because we're going to have to kind of flick back and forth here. So, right, what I'm going to do is just find all the values here. So we've got a number there, got a number there. Let's just find all the numbers here. This is all the stuff that we need to use. So where we're going to start, I'm going to start with working out moles, like we always do with these calculations. And this is where we're going to start with the manganate, because this is the only thing that we've got. We've got both the concentration and the volume. Okay, so that's where we're going to start with this one. So we're going to do 2.25 times 10 to the minus 2. That was the concentration. And we're going to times that by the volume, which was 13.2 centimeters cubed. So we're going to times that by 13.2 over 1,000. Right, let's do this. So 2.25 times 10 to the minus 2 times 13.2 divided by 1,000. And we get 2.97 times 10 to the minus 4. Okay, and that is the moles of the manganate. Okay, and so what we would normally do then at this point is we'd look at the equation and see what the ratio is between the manganate and the vanadium, and then work out the moles of the vanadium, right? But we can't do that because the whole point of this is they want us to work out what the equation is. They haven't told us the equation. So we can't do that. That's a bit awkward. So let's go back here and see what we can do. We've used this number, haven't we? We've used that number. This 10 and 50 centimeters cubed here, there's a 50 there as well, but that's just the same. That's just the same 50 as that one. That's the same thing. This is just the working out the number of moles thing. There was 10 centimeters cubed, but we're going to have to go back to the original 50. So at some point we're going to have to times it by 5. So the only thing we can do then is, if we're trying to work out what the equation is rather than work out the moles and then use the ratio to get back to the moles of the other thing, what we need is, if we know the moles of the two chemicals, we can then work out the ratio. So this is what we're going to use. We're going to use the mass of vanadium to work out how many moles of vanadium we had. Okay. So we're going to do 0.126 grams. 0.126 grams divided by the atomic mass of vanadium, which is 50.9. So 0.126 divided by 50.9 is 2.48, let's call it, times 10 to the minus 3 moles of vanadium. So what we now know is we now know the moles of each of them. So if we do one divided by the other, that's going to get us the ratio. Okay. But before we do that, we need to be careful because we need to include this factor of 5 that we were talking about before. So this is, we've used that, haven't we? This was the number of moles of vanadium, and that was in a 50 centimeters cubed solution. Then they did some sort of reaction with it. It was still 50 centimeters cubed, but then they only used 10 centimeters cubed of it when they reacted it with the manganate. So this is not the number of moles that reacted with the manganate. This is 5 times too big. We need to divide this by 5 to get the number of moles that actually reacted with the manganate. Okay. So that was the moles of vanadium in 50 centimeters cubed. So if we then do 2.48 times 10 to the minus 3 divided by 5, that's going to get us the moles in the 10 centimeters cubed that actually reacted with the manganate. So I've got this number still on the calculator from before, so we're just going to divide that by 5. It's 4.95 times 10 to the minus 4 moles of vanadium in the 10 centimeters cubed that actually reacted. So now we want to do the ratio between this number, it says, so we want to look at what's the ratio between this one and this one. Okay. So to do that, we're just going to do 1 divided by the other. Okay. I just want to go and check that that was a proper number, so I'm going to save this on the calculator. So this is now in A, and let's just go back and recalculate that. 13.2 divided by 1,000 times 2.25 times 10 to the minus 2. Oh, okay, that was right. Okay, let's put that in B. That's now B. Just get the right number there, didn't I? Yeah. So it's that one divided by B. And we get a ratio of 1.666. So that's kind of annoying. So if we say, let's do this here. So we've done this number divided by this one is 1.67, isn't it? And that should ring a bell, that number. What that is 1 2/3, isn't it? 0.67 is 2/3 as a fraction, or that is therefore 5/3. So what that's telling us is that it's a 5-to-3 ratio. So the ratio of, now we just need to be careful, this was the vanadium, wasn't it? Of vanadium to manganate is 5-to-3. Okay. Right, so therefore we can start to write our equation. Let's just copy the half equation. We've got one of the half equations from here, so I'm just going to copy that in place here. So we've got MnO4 minus plus 8. I'm just copying this from the other page, so we've got it. Right, and so if this equation has got 5 electrons in it, if it's a 5-to-3 ratio, what's happened is this has been times by 3, hasn't it? And so the other half equation would be times by 5 for the 5 electrons. So it must mean that the half equation that's got the vanadium in must have 3 electrons in it. Okay. So let's just see what was going on. It said in our other half equation, Vn plus is oxidized back to VO3 minus. So we must have Vn plus here, and it's going to make VO3 minus, and it must be plus 3 electrons. Because this is where we're going to get our 5-to-3 ratio from. We're going to then, to make these electrons balance, we're going to times this one by 5, so we'd have 5 vanadiums, and we're going to times this one by 3 to get 3 manganates, and then we'd get 15 electrons. Okay. So now we can work out this half equation. Here, it actually already told us in this VO3 minus, it's oxidation state plus 5. So therefore, if it's, what's it done? It's lost 3 electrons to get to there. So it must have been oxidation state plus 2 before. Okay, so that gives us our N. N is 2. And then we just need to end up writing the overall equation. But let's do this half equation first. What we've got here then is we've got the vanadium, we've got the electrons, that's fine. If I've got 3 oxygens here, then I'm going to balance that by putting 3 H2O here. And then I'm going to then have 6 H plus on this side. And let's just make sure the charge is balanced. There's a 2 plus charge here. And then 6 plus, take away 3, take away 4. Yeah, good. So now when we come to add these together, we want to do the overall equation. Remember, we're going to times this by 3, and then we're going to times this one by 5. So I'm going to end up with 3. Actually, let's write this under here because we can do a bit of tidying up as well. So I'm going to get 3 MnO4 minus plus 24H plus. I'm not going to write the electrons because they're going to cancel out, aren't they? And then I'm going to times this by 5, so I'm going to have plus 5V2 plus, because that's now, we know this is now a 2, plus 15H2O gives me 5VO3 minus, the electrons are cancel, times this by 5 as well, plus 30H plus, and then this top one, we times it by 3, hadn't we? So it's 3Mn2 plus 12H2O. And then hopefully you can see we can do some cancelling of waters and we can do some cancelling of H plus ions as well. So to do my final equation, we're going to have 3MnO4 minus. The 24 H pluses are going to cancel. And we're going to turn that into a 6. So they're going to all have gone. That's going to be there. And then the waters can cancel 12, so that's going to become 3. And that's going to go, so we're going to have 3H2O goes to 5VO3 minus plus the 6H plus once we've cancelled it, plus 3Mn2 plus. Right, and let's just do a final check here that the charge is balanced. So I've got 3 minus and 10 plus, so I've got 7 plus on this side. I've got 5 minus and 6 plus, that's 1 plus. And 3 up to 2 plus, so I've got 7 plus on that side. Okay, we're there.